Okay. So, raise your hand if you did the pre-lecture reading.
It was none.
I saw hands go up. I was like, no, you didn't. Yeah, I didn't put any pre-lecture reading up, and that was my. It was my bad, but at the same time, and I will put one up actually, strangely enough. But we're basically going to do what we did last time, but we're going to do it for QCD. So there, that was your pre-lecture. That was your pre-lecture sentence.
By pre-lecture reading, I assumed that you meant your resignation.
Oh yeah, no, thanks for that. Yeah, I keep threatening to have Vince Quoker to teach this course, which would be not only hilarious, but hilarious. Okay, so sit it down now, sit it down. Okay, so it might not be from the little bit that you know about the strong interactions, the weak interactions, and electromagnetism. It might not seem that there's any reason in the world why they would be related. After all, electromagnetism is kind of the engine that drives everything that we do. Most of the things that we think about, a lot of what physics research is about, you know, it gives you circuits, it gives you electronics, it gives you magnets, it gives you atomic forces that hold atoms and molecules together. But the weak and strong nuclear force, they just don't seem to rear their head in quite the same way. And so you might off the cuff think there's no way that they would, you know, bear any resemblance to each other. But in fact, this is the point of this course, sort of this unifying idea, they are very much the same kinds of things, okay? And what we're going to be able to do today is see what they have in common, which is essentially their fundamental structure, but what it is that's different about them that is largely responsible for why our experience with these forces is very, very different, okay? So to recap what we found about electromagnetism from last time, building it as a gauge theory, is that we constructed a gauge invariant Lagrangian from the Dirac equation by modifying the derivative in a particular way. And then we all right, where this guy, remember secretly, is h bar c psi bar gamma mu d mu psi, where we've defined d mu to be d mu plus iq a mu. All right. And this guy is f mu nu, which we finished last time by saying you could construct this as minus I over q times the commutator of covariant derivatives, which in this case turns out to be just d mu a mu minus d mu a mu, the familiar field strength tensor from electromagnetism. And then the point of this whole construction is that this is invariant under the following sets of transformations. Psi goes to e to the I q phi, where phi is position dependent. It's a local transformation. Psi bar goes to essentially psi bar e to the minus I q phi. But the non-trivial piece is that d mu psi also transforms with an overall factor of e to the I q to the minus I q phi d mu psi. Okay, so this was the very special property of the new derivative that we created. And you can see how this property allows this thing to be invariant. Because when I transform this guy and I transform this derivative of psi, those two terms will cancel. Or sorry, hold on, that should be a plus. Okay. Oh, and lastly, there's the transformation of the gauge field itself, which allows all this to happen. This thing goes to a mu prime, which is a mu. Can't write this low, I'm too tall. D mu 5 x mu. Okay, so there it is. You can put a box around that and say that's electromagnetism. That's all you ever need to know. Go home.
Where do you want us to leave?
No, I don't want you to leave. I want you to go home. Okay, so I write this on the board because we're going to write a lot of stuff that's very similar to this Okay, well, there's going to be a few key differences. So to get started with QCD, and I'll see if I can make this fit on this side of the board. That means it won't. The strong interactions, which I've made this statement before, and now we're going to see the technical details of it fleshed out. The strong interactions are based on a local SU3 invariance, where remember we identified this as a U1 transformation. This guy right here is a complex 1-by-1 matrix that happens to be unitary, so let's just call it what it is. It's a U1 transformation. It's local. QCD, quantum chromodynamics, is based on local SU3 transformations acting on quarks only. Now, electromagnetism affects anything that is electrically charged, and so when we write this Lagrangian, depending on whether our field in question has a charge or not, we just set Q to 0 or whatever. Okay? Here, it's essentially the same thing. You can think of all of the leptons, the electron, the neutrinos, the muon, and the tauon, as just having 0 color charge, right? And the quarks having non-zero color charge. But anyway, if we're going to consider this local gauge symmetry acting on quarks, then to follow the recipe that we used for electricity and magnetism, we have to start with a Lagrangian for quark fields. But we know a Lagrangian for quark fields. For free quark fields, that's just a Dirac Lagrangian. Okay? So our starting point will once again be the good old Dirac Lagrangian, which represents free, that is non-interacting, spin-a-half fields, and we would just, for the context of the strong interactions, we would want psi to be a quark. So we could say it's a down quark, or an up quark, or strange quark, strong quark, top quark, bottom quark, it doesn't matter. Okay? Here's the first change over what we did here. In the electromagnetic case, we were able to make a transformation of this form by multiplying by a complex number because the psi's themselves were, Kellen? Where are you, Kellen? What feature of the psi's allowed us to consider a transformation of this form?
They're also able to be complex.
Yeah, they were complex. Okay, the psi's, the spinors in the Dirac equation were complex. In fact, I made the point that anytime we have a complex field, we can consider a transformation of this form. Okay. Here, though, how are we going to enact an SU3 transformation on this thing? I mean, if it's a number and we're trying to act on it with a 3-by-3 matrix, that doesn't really make sense. Okay, so unfortunately, we're going to have to make psi something a little more complicated. All right, so psi, for these purposes, is going to have to be a 3-component vector. Okay, the components of psi we will call psi red, psi blue, and psi green. Hence the name QCD, quantum chromodynamics, although this has absolutely nothing to do with frequencies of electromagnetic radiation. They are not red, blue, and green. Those are just labels. Okay? Because we have to label 3 things.
Is there a reason of the choice red, blue, green? Or is it just 3 colors?
It is, I could have called them Fred, Smiley, and Batman symbol. But there is a certain sense in which people like to think of an admixture of all 3 as being colorless or white, and we'll talk about that. But it's just a mnemonic. It literally doesn't, yeah, you could have called it anything. Okay? But it's hopefully it's obvious that there needs to be 3 things, right? Yes?
Well, it just seems to me that we said there needs to be 3 things because we're working with SU3.
Sure.
How do we know that we're working in SU3 with quarks?
Okay, so again, to motivate this, you actually have to look at experimental data. So you start doing experiments and you start noticing that you, for example, get resonances in sets of 3. And so the number 3 pops up a lot in the experimental data that whenever you're doing interactions with quarks. And then you backwards engineer the theory. we're not doing the course that way because I find it very confusing. I'm just giving you the theory. So you kind of have to take me for my word that this symmetry group acting is going to give us the correct Lagrangian that describes the interactions of quarks through quantum chromodynamics.
Just kind of a random question, but if I have a quark or a set of quarks, is it possible to know which combination of red, blue, and green they are?
If you have a particular quark, you will never have a particular quark.
Well, what I meant is like an atom or a collection of, is it possible to discern the three color charges?
So the only states of quarks that exist are colorless, and that's a whole discussion we're going to have later in the course.
Okay.
So you're always going to have a combination of things. It can be a combination of all three of these, or it can be a red, anti-red pair. Okay. They're always going to come in colorless combinations, but that's something that we can prove, and we'll discuss later on. Okay. Now I want to stress something before I get started on this. In electromagnetism, we're used to thinking of charges, being plus or minus the fundamental electron charge. So we say an electron has charge E, a proton has charge minus E, if you take E to be the negative charge, okay? These are two different things. This is two different values of the electric charge. It's still one kind of charge. It's just two different values of it. These are three different kinds of charge. Okay? It's not like there's one kind of color and red, green, and blue are different values of it. These are different kinds of charge. Each of them can take different values. So for example, we can have red and anti-red, we can have blue and anti-blue, and we can have green and anti-green. That's the analogy of plus and minus for electric charge. So they're different. It's almost as if you've got three copies of electromagnetism. And in fact, in a certain sense you do, and this is sort of a technical group theory thing, but anytime you have a group and you want to sort of pull out the overall electromagnetic story of it, what you do is you decompose it into its maximal commuting subgroup or its Arcan subalgebra. Those are all fancy words, but it essentially says the largest abelian subgroup, that is a subgroup, a proper subgroup of this thing, where all of the factors commute, is U1 cross U1 cross U1, and that's three copies of electromagnetism. So they have three different kinds of charge. Okay. All right. Now, what I'm interested in doing is taking this Lagrangian and making it invariant under an SU3 transformation. So what does that transformation look like? Now let me talk about this a little bit, because you might say, well, I see some things that are familiar, but some things that are not so familiar. First of all, if you come back and compare it to the transformation in electromagnetism, you'll notice there's a sign change, a minus sign. Okay, that's irrelevant. That's conventional. I could have just changed the sign of Q. Okay, and I've also included a factor of H bar C. That's again conventional. All of that is just changing the definition of what we call charge. Okay, I'm adopting this because if you want to look at Griffiths, this is the notation Griffiths uses. And in fact, if you compare this discussion to Griffiths, you'll notice that Griffiths actually did this with a minus IQ over H bar C. Okay, so I'm going to try, since this is already going to be more complicated, and you might want to look at a reference, I'm going to try and use the notation from the reference. But it's just a convention. It's just sort of a definition of the constant piece right here. Okay. Now, what about the rest of this thing? Well, remember that if we think back to what we learned about Lie algebras and Lie groups, okay, nothing that we've covered in this course was useless. If we think back to all that stuff we learned about Lie algebras and Lie groups, remember if you have the Lie algebra associated with something like SU3 and you want to build an arbitrary group element, you use the exponential map. So the exponential map took the form e to the I GAVA, where GA is the vector of matrix generators of the group, and the VA is the vector of parameters. So each generator of the group corresponds to sort of the individual ways you can transform. Well, so for example, we talked a lot about rotations in 3 dimensions. You can rotate around X, Y, and Z. So an arbitrary rotation is some amount around X, some amount around Y, some amount around Z. So you have a vector of parameters. Each one tells you how much you're doing each of the fundamental sort of transformations you can do. Yes?
So then here the equivalent would be changing red, changing blue, changing.
Well, we're essentially yes, but we'll come to an interpretation of it at the very end of the lecture. Okay? But yeah, essentially, it's changing color. Okay, so with this in mind, we can now identify what some of this stuff is. So lambda is going to play the role of GA. That is, lambda is going to be the set of generators for SU3. And Brandon, how many generators of SU3 are there? Do you remember?
6.
It's close. It's not infinity.
Oh, it's n squared minus 1.
It's what?
Isn't it? That's the number of free period.
So, yeah, 8. I heard 8. It's n squared minus 1 for SUN. Okay. So there is going to be 8 generators, and those are just going to be represented by 3x3 matrices. In fact, you've seen these matrices. Anybody remember where you worked with the 3x3 generators of SU3? Homework 3. Okay. I'll be alluding to, you don't have to remember it, but I'll be alluding to homework 3. So the explicit expressions for those are in your homework 3. The phi is going to be the parameters. So we have 8 parameters. Now this is important for me to identify what these things are, because for example, these things you can think of as numbers, but these are matrices. Okay? I know it's a vector of numbers, but each element is a number. But each element here is a matrix. And one of the things we're going to find today is we've got to be really careful when something is and isn't a matrix. All right? And then last but not least, we can identify minus Q over H bar C as what we're just going to call the coupling. So I'm henceforth going to just call that Q over H bar C G. It's going to get cumbersome to keep writing that. And this coupling is going to determine how strongly the quarks interact with via the strong interaction. Now you might think to yourself, this is automatically a place where you might ask a question, wait a minute, you have 3 kinds of charge. Wouldn't those 3 kinds of charge give you 3 different couplings? After all, for electromagnetism, the coupling here in this transformation was the electric charge, but the electric charge tells you how strongly charged particles couple to the electromagnetic field. Why do we only have 1 coupling for the strong interaction? Well, the key is as I think Martin said, what the strong interaction transformation is going to do is they're going to mix up red and blue and green. But it's a symmetry of the theory. And if you had red, blue, and green coupled differently, and then you have transformations which mix them up, there's no way that's going to be a symmetry. Okay? So we do have 3 different kinds of charge, but they all couple equally with equal strength. So there's really just 1 overall coupling for the strong interactions. All right? Okay. Here we go. So, yeah.
So is there a reason why, like, you've been using coupling for the last, like, couple minutes? Is there a reason, like, because I'm very confused, like, because I've heard coupling before, but, like, why, how's it different from being, like, in a balanced state? Or, like, a stranded, like...
A balanced state's just a particular solution to things, but coupling... So, how do we identify interactions in a Lagrangian?
Cross products.
Yeah, you're going to find products of fields. Whatever the coefficient is how strongly these fields couple to each other. For example, if this is 0, There's no interaction. Okay, so when I refer to the word coupling, I'm literally meaning how strongly are the fields sort of interacting with each other. And of course, we're going to see this kind of term pop out of this, as we did with electromagnetism. Okay, so here we go. Let's make this thing locally invariant. Okay, right now, this is a global transformation, right? So if I come in here and I sort of, I'm going to write this now as just G. You can remember that G is Q over H bar C. Then what I'm interested in doing is promoting this to now a symmetry. Oh, well, by the way, before I do that, let's erase that. Is it obvious to you that that is a symmetry of this Lagrangian? Joe says no. See that, Joe? No. Okay, so let's go through the argument. If psi transforms this way, psi bar prime would transform with that factor. That's the same argument we made last time for electromagnetism. But if I plug this in for this guy, since this is constant, I can just move it across the derivative, and then it will cancel with this guy coming from here. And then the same cancellation will happen with this pair. Okay, so this is globally symmetric for very much the same reason that our starting point in electromagnetism was globally symmetric under this U1 transformation. Yeah?
How can we be sure that it commutes with the gamma mu? Or are you looking at the gamma mu, T mu, and
Well, why would it not commute with gamma mu?
because it's a matrix?
Okay, so we have to be very careful where our matrices live. Gamma mu is a matrix in. Lambda is a matrix in color space.
What?
Well, what is it acting on? It's acting on a vector of colors. Okay, so I know. And I'm going to try and keep referring to color space, spin space. But does this answer your question now? This is a matrix in color space. This is a matrix in spin space. They don't care about each other. Okay, so I can freely move that past gamma. Sorry, guys. I know. Okay, so are we all in agreement that this is a global symmetry? Yes.
So I get what you're saying about it's a matrix in color space, but isn't it still acting on a spinner?
Sure, yeah.
So why isn't it in spin space if it acts on a spinner?
Oh, so, okay, so this right here is a 3-component vector of 4-component spinners. When I do a color transformation, I'm only taking each of these have 4 components, but I'm taking those 4-component blocks and I'm reshuffling them. That's all the color cares about. If I do a Lorentz transformation, it's going to take this guy right here and mix his components, separately take this guy and mix his components, and separately take this guy and mix his components. So the two operations are disconnected, even though they can both be enacted on the same thing. Okay? Yes?
The 4 components of psi red, psi blue, psi green.
Yeah.
Those are not space-time components. What are they?
The 4 components of psi?
Yeah.
It's a Dirac spinner. It's the 4 components of a spinner.
Okay.
So it's not 0, 1, 2, 3. It's rather this. So remember, to get the Dirac solution, we had to take the space-time coordinates and pair them up in these complex pairs, and then we ended up with still a 4-component object, but the 4 things do not correspond to time x, y, and z. So you should go back and look at our sort of original analysis of spinners to see what those 4 components correspond to. But yeah, it's it would be nice if we lived in 5 dimensions so that the spinners would have a different number of components than the space-time dimension, but we don't. We live in 4 dimensions. God hates it. So anyway, did I see another hand?
Sort of just close God.
Didn't Einstein make his Einstein summation notation so we wouldn't have to deal with like vectors of matrices of vectors and stuff like this?
Sure, and the truth is I could do all of this in index notation.
Nobody does though.
Can you imagine having indices for every single different, first of all, I'd run out of letters. But literally, that's why people don't do it, it's just there's so, but the thing is you don't run into that many different kinds of objects like you do with the space-time indices. The space-time indices are so many different kinds of objects, it's actually a good idea to use indices. But for spinors, for these color transformations, you're always kind of seeing the same combination, so you can almost just sort of leave it understood. So like I said, you know, for spinors, if I want to make a scalar, I'm always going to start with a sandwich, and then any other kind of matrix I stick in here, everything will be taken care of, as long as I just remember permuting things. It's not necessarily trivial. So, yeah, you can do it with indices. It's just ugly. It's really ugly. Okay, so here we go. I want to promote this to a local symmetry. And to do so, we're going to change the derivative. Now, the change in the derivative is going to be analogous to what we did for electromagnetism. Okay, so in electromagnetism, we just added IQ times this new field A mu. You might say, well, what's this? Well, we actually have to add 8 gauge fields. We have to add 8 gauge fields because there are essentially 8 distinct transformations that we're trying to localize. So one way to think about it is, if I go back to this notation, if an arbitrary SU3 element looks like that, I could start by saying, I want to consider just the transformation which acts on the first index. So this is like only looking at rotations around x and forgetting about y and z, and then making those local. To do that, you would have to add a gauge field. And then next, I could come and say, okay, now I want to consider the transformation around the next axis, and I would have to add a gauge field to make that local. And I could repeat this going through all of the different independent transformations, but each time I would add a gauge field. So I'm going to need 8 total, because I have 8 independent generators. Okay?
So is that a dot product?
So, right, so this dot, when I write it, corresponds to a gauge field for each generator. And later I will actually use an index. Okay, so you can also think of it as there's a color index A that runs, not a color index, a generator label that runs 1 to 8. Yeah?
Do you have to define the mean covariant derivative every time you have a different field?
Every time you have a different field here?
Yeah, because like it looks like there's every time we do a different one, there's going to be a different Castellani's of mu.
Every time you, so fortunately we're only going to do this 3 times. For each force, you introduce a different covariant derivative.
We don't have to for like any other field, it's just the forces.
It's just the forces. So you have to introduce a covariant derivative when you want to make a symmetry local. But we only make 3 symmetries local, and each of those symmetries gives us a force, because there are 3 forces in the standard model, and I'm of course excluding gravity from this conversation. David?
So I'm wrapping my head around it. That's 8 gauge fields, each made up of 4 components. So it's like a vector.
Yeah, I mean it's got a mu index, so it's a space-time vector.
I'm sorry, I thought gamma mu was a space-time vector of spinor matrices.
Yes.
Oh, okay.
I mean, a particular gamma mu is a matrix in spin space, but it's a vector of matrices. Yeah. Okay, so, all right. There I am. Okay, so what we want, just writing this doesn't do anything for us, okay? I mean, I can stick that in, but ultimately, what I'm hoping to achieve is to get this thing to be invariant under this transformation. And as we talked about, sort of at the last part of the lecture over E and M, is that what we're looking for, what we want, is for this covariant derivative acting on the spinor psi to transform in a nice way. That is, we want it to transform with an overall factor of that. Okay? It's exactly what we wanted here. Okay? Because then when I look at this, when I look at this modified Lagrangian, and I transform this term, I'm going to pick up that factor, and then that will cancel the transformation from psi bar, which will be this factor with a plus sign. Okay, that's what we want. Yes?
Should phi of the exponent be a function of x?
Yeah, sorry, I'm gonna probably suppress that. But we are now localizing, so phi will always be a function of position now. Okay. So the question is what do we need to have happen so that this is the case? Well, let's just go through this. If I actually take d mu psi and I write it out, I just copied down what I wrote right here, but acting on psi, and then I transform it, then this becomes d mu psi prime plus ig lambda dot a mu prime, because that a mu has to be transformed. And now I can go in and write down what I know about the transformations of psi. Okay? So I have d mu e to the minus ig lambda dot phi psi for this guy, and then plus ig lambda dot a mu prime e to the minus ig lambda dot phi psi. Again, phi depends on space-time. I'm just going to suppress that. Okay? I just transformed psi. But now, of course, this derivative is going to do something to this exponent because there's dependence on spatial position in phi. Okay, so if we actually expand out what that does, it's not the end of the world. All right. Now, if you stare at that for a minute, what we want is for this to give us back what we started with. That is, we want this, we want it to give us back an overall factor of e to the minus ig lambda dot phi times what we started with. That's what we want. So what do we need a mu prime to be in order for this thing to become this? Can you see it? Okay, you stared for a second and I'll write it down, and I now want you to convince yourself. So if lambda dot a mu prime is e to the minus ig lambda dot phi lambda dot a mu e to the ig lambda dot phi plus I over g d mu e to the minus I g lambda dot phi e to the ig lambda dot phi. All right, let's just go through the pieces here and see if we can see this. If you literally take this expression and pop it in right there, okay, the first term is going to take this guy, cancel that guy, and give you back an overall e to the minus ig with this just being a normal a. And that's what we want right there, okay? This term, when I throw it in, okay, this far guy is going to cancel that transformation, and then this derivative piece is just going to cancel off that guy. No, sorry, it's going to cancel off, yeah, this guy. Okay, everybody see that? Now, compare that, if you will, to the way that A transformed in electromagnetism. Looks worse, doesn't it? But I want you to notice something. In electromagnetism, these transformations here were one-by-one matrices. They commute. Everything commutes. You could have written down the transformation in electromagnetism in exactly the same way, but then what you could have done was said, but this is a number, I can just move it past this and cancel this guy. And then this is a number, I can take this derivative, that will give me back the exponential, I can cancel it off of that, and then I'm just going to be left with the derivative of the parameter. Okay? So for an abelian symmetry like U1, all of these exponents can be combined and canceled because you can move things around without worrying. We cannot move these things around because this is a matrix in color space. 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 We can't just freely move things around. Okay, so we have to leave that expression as it is. You good with that? You guys are leaving again?
Last time.
Okay, so putting this guy into our Lagrangian, you're now going to notice, and let me just, yeah, I think we can get rid of this now. Putting this into our Lagrangian, so let me actually put in the form of this. We have d mu psi plus ig, and I'll just write it this way, psi bar, or ig h bar c, psi bar, gamma mu, lambda dot, a mu psi, plus mc squared psi bar psi. Okay, that's just sticking in our new derivative, but writing out both terms. What do we see arise? Interactions, exactly. We have a product of the spinors that we started with, the quarks, with these new gauge fields. Okay? So the gauge fields, it might come as no surprise, are what we call the gluons of QCD. They're the gauge bosons that allow this SU3 to be a local symmetry. They are the analog of photons in electromagnetism. Okay, remember photons represent for us the potentials that you eventually build electric and magnetic fields from. Here, the analog are the gluon fields. Okay? And we've been forced to introduce interactions in order to make the symmetry local. In exactly the same way that we found for electromagnetism. Yes?
And the n in the Lagrangian there, that would be the mass of the quarks?
Yeah, so this is the mass of the quark fields. The mass terms are always going to be mass of whatever these fields are, and the size are the quark fields. The A's are the gluon fields.
Somewhere in the A mu would be a mass of the gluon?
Well, we haven't talked about that yet. That's what's coming next. So the final part of the story, remember for electromagnetism, we gauged the U1 symmetry. We made it local and we generated these terms. But then we said that that new field is not really dynamical yet. It doesn't have its own kinetic energy term. And so we then looked to the Proco-Lagrangian But we also made this argument that we couldn't have the mass term from the Proca-Lagrangian because that mass term for the gauge field violates the gauge invariance we're trying to have. We're going to find the same result for the gluons. The gluons have to be massless. Okay? But constructing this term is going to be a very interesting part of QCD, and it's going to give rise to a lot of the interesting effects. So that's what we're going to do next. I saw a hand go up, so go ahead and 3 hands. Good God.
Does the equation say anything about how many quarks there are?
How many different kinds of quarks there are? No. Well, it says that for a given quark species, that is an up quark, you have 3 colors of it, red, blue, and green. It doesn't tell you how many different quarks there are. That's a completely separate issue. The weak interaction, when we come to it, will tell us that the quarks always appear in pairs, doublets, up, down, strange charm, top, bottom. But talking about why there are 3 generations is even a step further removed. Okay, so no, this analysis doesn't have the answer to that question.
Is this the complete Lagrangian?
No, I'm trying to get there. So yes?
Can you construct the kinetic term from the covariant commutator?
Yeah, that's what I'm going to do. That's what I'm going to do. I'm not stop looking at you guys. Sorry. Okay, so we want to add a kinetic term for the quark for the gluon fields. And to add that kinetic term is where we're going to get some very interesting stuff. Now, again, when we talked about electromagnetism, we just kind of grabbed the Proca-Lagrangian and said, oh, we can use that because that's the Lagrangian for a vector field, where f mu nu is defined like this. But at the very end of the lecture, I said it would actually be better for us to define our f mu nu by the commutator of covariant derivatives. And the reason why that's better is because this is guaranteed to be gauge invariant. Okay? Unfortunately, this is only gauge invariant for the U1 case. If I just wrote this down, it would not be gauge invariant for SU3. But if I allow myself to define it in terms of the commutator of covariant derivatives, it is gauge invariant. So I'm going to construct this bad boy, f mu nu, by taking I over g times the commutator of the covariant derivative. Okay, and here's the covariant derivative hiding right here. But in order to sort of extricate what this thing is, I have to let that act on a field psi. Because there's derivatives in there and it's hard to keep track of what's happening unless you let it act on something. So writing this out, and I'm probably going to skip a lot of steps here. It's actually not so bad. Here we go. So there's my covariant derivative for d mu, acting on the covariant, or multiplying the covariant derivative here, but I'm going to go ahead and let this act on psi. Okay, so that's the first order, and then I subtract the reverse order. Okay, so all I've done is wrote down the covariant derivative twice in reverse orders for the mu and nu indices. The second one, I went ahead and acted on psi with it. And now if you expand this thing out, you're going to get this ginormous host of terms. But there's a lot of love in there. So first and foremost, and I'm not doing this maybe in the most natural order that you would multiply this thing out, but I'm going to write it down in a way that's convenient to see the simplifications. There's nothing deep about that, guys. I just, multiplied this out. You've got derivatives acting on products of things, so you got to use a product rule, and you just expand the living crap out of everything. Okay, and you generate that set of stuff. Okay, here we go. Bam, bam, partial derivatives commute. Bam, 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 bam. All of those disappear, so this is what we're left with, right? Now you might say to yourself, ooh, these cancel. Can you say that? Why not? Because this is a matrix in color space, this is a matrix in color space, you are not allowed to just flip them. If you could, yes, that's what cancel, but you can't. Okay? So we're going to have to contend with this term. This is going to stick in, stay around, but it's going to give us some interesting effects. Okay? So, to write this in a slightly more compact notation, I can say that now I can just get rid of the psi everywhere and use this to define f mu nu. My f mu nu is now going to be d mu lambda dot a nu minus d mu lambda dot a nu plus ig lambda dot a mu lambda dot a nu. Commutator. Okay? Everybody sees the commutator structure here? Might as well call it for what it is. Now lambda dot a mu, remember this is a dot product in color space. Or sorry, it's not a dot product in color space, it's actually a dot product over the space of generators. So there's 8 generators, 8 gauge fields, so you can think of this as lambda a mu a, where a is 1, 2, dot, 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 8. Okay? And if I think of it that way, then f mu nu I can write as follows. Lambda a, I can just pull the lambda outside of this derivative because the lambdas, the generators, are just matrices of constants. So I can say lambda a d mu a nu a minus d nu a mu a plus ig lambda b lambda c a b mu a c nu. Okay? So if you literally come in here and you write this guy as BD and you write this guy as CC, these things are not matrices. Okay, they're vectors of numbers in this space. But these are matrices. So these I can pull out of the commutator. But the lambdas have to stay in the commutator, right?
Wait, can you explain that again? Sorry.
So the reason this is a commutator, the reason why it's not 0 is because you've got these matrix things sitting in there. But the matrices are the lambdas, not the A's.
Okay. We can think of the A's in this case kind of just as a number.
Yeah. A component of A is a number that is paired with, it's a number in this generator space that is paired with a matrix generator. Okay, so now if you actually reference homework 3, you don't have to do it, I'm going to write it down, but what you worked with in homework 3 was exactly the Lie algebra of SU3, where you said, okay, if I take 2 generators and I form their commutator, that's I, F, I, J, K, G, K. The up and down doesn't really mean anything in this context, so. So here we can see the lambdas are the generators of SU3. So I might as well write this in the notation that I'm using now. So I can say that lambda A, or lambda B, commutator with lambda C is I, F, A, B, C, lambda A. Okay, and you could write this as BCA, but you can always throw the A back in front. Yes?
So is there meaning to where the index goes on the lambda matrices? Because you're calling an inner product with two uppers, with an A up top for the lambda and an A up top for the A. So I guess I'm just not clear on why the inner product, you can have the A on top for both of the things in the inner product. If you go off a line or two, you have lambda, yeah, right
Here?
Yeah.
So why these are both upper?
Right. But
We don't care about upper and lower.
It's
So
just-
essentially the metric on the space is the identity, so we don't worry about it. And if you don't need to worry about it, I'm not going to.
Okay.
It's only space-time indices, mu, nu. Those are the only ones where we really have to be careful about upper or lower because the metric is not the identity.
Do the gluon fields commute with the lambda matrices?
Do the gluon fields commute with the lambda
Does A commute
matrices?
with lambda?
Yeah. Yeah, that was the discussion I had with Jacob about why you can pull these out.
Okay. Does A commute with itself? Like, does A mu commute with A mu?
Yeah. Okay, with that in mind, and now I'm going to just write some results down and you're going to get to fill in the details. I was going to do it for you, but so many good questions, I'll let you do the homework. So now our F mu nu, we can write as lambda A, and again, d mu A nu minus d mu A mu. And then putting in that expression, minus G F A B C lambda A B mu A C nu. Or there's a lambda A in all of this. So I could just refer to the 8th component of mu nu as that. And then what I wrote before was basically this. Okay. Now I wish that was the end of the story, but remember that's not the Lagrangian. That is the Lagrangian. We have to square this. Okay?
You say we didn't.
I know. If we square it, we get this we get a bit of a beast. But first of all, we've got to make sure that the thing that we're constructing is gauge invariant. We don't screw up what we tried to achieve in the first place. And it might not be entirely intuitive that it's the case, but at least, you know, from experience in the past, as long as this is a dot product over the components, remember this is a component for each of the A's, as long as this is summed over that, then that's going to be gauge invariant. Okay? In the same, I mean, I'm just saying, like if you sum over the squares of all the components of a vector, you get its length, and that is invariant into rotations. It's an analogy to that. Okay. If I write this out, oh good golly, I'm just going to write out what it is in the end. Okay. We literally take this. We literally take this expression, the whole thing, plug it in right there. We take the entire expression and shift every mu and nu up and plug it in right there, and then we multiply the hell out of it. Okay? And I'm just going to write down what you get in the end. You get this guy. Which you might have expected. But you also get these guys. And again, I skipped one step of actually plugging these two things in here, and if you look at the notes, you'll understand why things are labeled like they are. Okay. So in principle, we now have the entire QCD Lagrangian because you take this guy and you add that to it. All right, that's exactly what we did for the electromagnetism case, all right? It's just that this expression is more complicated than the electromagnetism case. But notice, okay, this is exactly what we would expect here. Everybody see it? Yeah. If I take this and I f mu nu, I'm just going to get this roughly times the same thing with the upper indices. So this is the kinetic term for the gluons. What are these? They're gluon-gluon interactions. They're products of gluon fields and with derivatives of gluon fields. They're interactions. So what we've just discovered is that very much unlike photons in electromagnetism, which do not interact with each other classically, gluons interact with each other. And the reason they interact with each other is because these Fs are not zero. That is because it is a non-abelian group. So all of this work we did talking about abelian, non-abelian, why is that important? Well, it's very important for the interactions because if you have a non-abelian symmetry, you get some really weird effects. You get that the gauge particles interact with each other. This leads to weird things. For example, you can take away all the charged matter in the universe and just have pure QCD, and it can still do shit. You can create glue balls. Ultimately, the presence of gluon-gluon interactions is going to help us understand why you can never see bare quarks. Okay, why the strong interaction coupling gets small at short distance and large at long distance. Okay, but you can clearly see now that we're going to see an analogous thing for the weak interactions because you know that SU2 is non-abelian, so you have to have the same sort of thing pop up. All right? Yeah.
Is the interaction from the ADAE or the ADWAA?
Sorry, is it?
Is it because we have those first two, or is it because we have, like...
All of these are different interactions.
Yeah, but is it because, okay, so in the second line, is it because we have those two A's in the beginning, or is it because we have those two A's combined with the del mu A?
Okay. So when we do Feynman diagrams, which is kind of the cleanest way to think about this is going to give rise to a 3-point interaction for gluons. So one of these would be an A, and this would be a DA.
Okay.
They're all three interacting at once.
Okay.
And this would be a quartic interaction, so a quartic gluon interaction.
Okay.
Four gluons interacting.
And when they have the same what color index, so like in that first case, the reason it's not an interaction is because they all have A's at the top?
Well, no, so this is an interaction of sorts, but it's interpreted as kinetic energy, as velocity. I mean, yeah, that's an interesting thing, but it's not, yeah, okay, it's actually what you're saying. I know what you're saying now. Yeah, it's because these A's are the same.
Okay.
So kinetic terms are always the field with itself. These are always going to be the field with a different version of the field, like a different color of the field. Yeah.
I understand. Thanks.
All right, I'll see you guys on Tuesday. And on Tuesday, we will talk a little bit about interpreting this in terms of color, which we didn't get to.
Yeah, my elementary school somewhere that's like